So some really nice quick factorial proofs for us here. So first prove that this thing here is this, and then I'll also prove this thing here is this. So pause the video, have a go if you want to. Otherwise, let's get straight into it. So when we're doing a proof like this, we can start on either side, but I'll start on the left. I'll say left-hand side equals this thing, which is, of course, well, what is a factorial? It's just the number times every integer below it down to 1, assuming these two numbers are integers, of course, which I'm going to assume that they are. Okay, well, this is nice because, of course, 2n goes through n plus 1 and n minus 1. So all of this will just cancel all of this, and I'll be left with this thing here, which seems like the most obvious thing to do straight away. But then you look at this and you think, well, actually, how on earth do you get this to be this? Right? This hasn't gone well at all. So you go back to the start and you have a quick rethink. How else could you do this rather than just doing it the very obvious cancelling way? Well, you can run it out like this, and notice I've written a few more terms here. And the key thing here is, okay, looking at this right-hand side here, where are these 2's coming from? I can kind of see where this product comes from, because there's going to be lots of odd numbers multiplying together on here. But where do these 2's come from, man? 2 to the n is 2 times 2 times 2, and so on. Where are they all coming from? Well, this top here, on the top side of this fraction here, otherwise known as the numerator, I guess, there's lots of even terms, right? This one and this one and this one, and I can factorize out a 2 from every single one of them. Right, so factorize out 2 from this one, a 2 from this one, factorize out a 2 from this one, and all the way down to the bottom, I can factorize a 2 from that to give me two 2's, a 2 from this to give me a 2 and a 1, and so on. And now what I can do is I can cancel this n with this n minus 1 with this n minus 1, this n minus 2 with this n minus 2, and so on, all the way down. This 2, or really this one here, cancels with this one here, and then this 1 cancels with this one here. And that leaves me on the top 1 times 3 times 5 times all of the odds up here, which is great, and it also leaves me with a bunch of 2's. Now, how many 2's exactly? Well, of course, there are 2n kind of things multiplying on the top here. I've taken out a 2 from exactly half of them, because if you have 1 to an even number, exactly half of them are going to be odd, half of them are going to be even. So there are 2n terms. I've taken out a 2 from half of them. That means I've taken out n 2's. So this top side here is going to be 2 to the power n times all of the odd numbers, which is exactly what was required. So that was quite an interesting one, and quite good fun. Now let's look at the second one that we were supposed to be doing, which is here. And I'm going to do something that's going to be quite helpful to know here, which is that when you're doing a proof like this, you can start on either side. So rather than starting on the left-hand side, why don't I just start on the right? And now what I noticed, based on my failed experiment earlier, is that this thing here is actually just 2n factorial over n factorial. I proved that by mistake. Well, not by mistake. I proved it and it didn't really lead anywhere. But I can write this as this, right? Just cancelling the rest of the n's and then this n, and you get this. Now, why is this helpful? Well, it's helpful because I can just do exactly what I just did. So I'm going to do that. I'm going to do exactly what I just did. And I'm going to get down to this, which is what I showed the first time. Now, how am I going to get to here? Well, what I can do is I can take all of these 2's at the front here, and I can distribute them. That shouldn't have come up first, but whatever. I can distribute them across each of to give 1 to each of these odd terms here, which of course when they multiply out is going to give me all of these even terms, which is equal to the left-hand side. And now how do I know that the last thing to check here is that, okay, I'm distributing out n 2's to each of these brackets. How do I know there are n brackets here? Well, there's probably much easier ways of thinking about it, but what I did was, if you add 1 to every single one of these brackets, you get 2, 4, 6, 2n minus 2, 2n minus 2, 2n. And then if you halve them all, you just get 1, 2, 3, 4, 5 up to n. So there are definitely n brackets here. That was some really hand-wavy logic, but whatever, I'm going with it. So when I distribute out these two 2's, there's 1, 2 for each and every bracket, which means when I expand out, I get this, which is the left-hand side. So yeah, some 2 really interesting proofs. It's kind of nice that despite the fact they look quite different, they were basically just the same proof, which is kind of interesting. I'm sure there are lots of other ways to do it though. But anyway, thank you for watching.